Hello, good day everyone. This time we're going to discuss some examples on definite integral, and we're going to solve them by substitution. The fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. Differential calculus arose from the tangent problem, whereas integral calculus arose from the area problem. We need to say the fundamental theorem of calculus links the relationship between differentiation and integration. The first part of the theorem shows that indefinite integration can be reversed by differentiation. It also proves that for every continuous function, there is an antiderivative integral. So if f is a function that is continuous on an open interval I, and if a is any point in the interval I, and if the function f is defined by f of x equals the integral from a to x of f of t dt, then f prime of x is equal to f of x. Therefore, the derivative of the integral of f of t dt from a to x is equal to f of x. The easier definition. Note that part 1 can be rewritten as the derivative of the integral of f of x dx, which says that if f is integrated and then the result is differentiated, we arrive back at the original function f of x. The second part of this theorem tells us how to evaluate a definite integral, assuming that f has an indefinite integral. That is, the integral from a to b of f of x dx is equal to f at b minus f at a. And to say we evaluate it from the upper limit minus the lower limit. We now formally define the fundamental theorem of calculus. It says, the first fundamental theorem of calculus, let f be a continuous function on the interval ab. Define f of x equals the integral of f of t dt from a to x for every x element of ab. Then f is an antiderivative of f on the interval ab. That is, the first derivative of f of x equals f of x for all x element of ab. Again, part 1 simply says that if f is integrated and then differentiated, we arrive back at the original function f. Part 2 of the fundamental theorem states that if we know an antiderivative of f, then we can evaluate the integral of f of x dx from a to b simply by subtracting the values of capital F at the endpoints of the interval AB. So we have the second fundamental theorem of calculus is given as follows. You have f be a continuous function on AB and f be an antiderivative of f from AB. Then the integral from a to b of f of x dx equals f of x from a to b, which is equal to, you substitute this value, the upper limit, to the function that you get, minus, you substitute this time, the lower limit. Here's a list of some differences between the indefinite and definite integrals. For the indefinite integral, the integral of f of x dx is a function of x. Whereas, for the definite integral, the integral from a to b of f of x dx is a number. By definition, the integral of f of x dx is any function of x whose derivative is f of x. That is for your indefinite integral. Whereas, for For the definite integral, the integral from a to b of f of x dx was defined in terms of Riemann sums and can be interpreted as area under the graph of y equals f of x, at least when f of x is greater than 0. For the indefinite integral, x is not a dummy variable. For example, the integral of 2x dx is equal to x squared plus c, and the integral of 2t dt is equal to t squared plus c. These are functions of different variables, so they are not equal. Whereas for the definite integral, x is a dummy variable. For example, the integral from 0 to 1 of 2x dx equals 1, and the integral of 2t dt from 0 to 1 is equal to 1. So, the integral of 2x dx from 0 to 1 is equal to the integral of 2t dt from 0 to 1. We have here our first example, that is, to evaluate the following definite integral. The integral of 5x cubed plus 2x minus 3 dx evaluated from negative 2 to 1. Recall the following integration formula, that is, the integral of x to the n dx is equal to x to the n plus 1 all over n plus 1. But this time we don't make use of our c because we have here definite values. So for the solution, we have the following. You have 5x cubed, because we have 5x cubed there, then you have 3 plus 1 will give us 4, and then all over 4. So you have 5 over x to the 4th. As for the integral of 2x there, you have 2x squared over 2, so you can divide out 2, so you now have x squared. And the integral of negative 3 dx is actually equal to negative 3x, evaluated from negative 2 to 1. Now recall again, how do we do that? That is, the integral from a to b of f of x dx is equal to f of x from a to b, wherein you can rewrite this to be equal to f of b, that is the upper limit there, minus f of a, the lower limit. So that when we substitute, we now have 5 over 4, our x is replaced by this time the upper limit, which is 1 raised to the 4th plus 1 squared. Then you have minus 3 times 1, okay, minus, from here, you have minus f of a, so the lower limit there, which is negative 2. So 5 over 4 minus 2 is raised to the 4th, so minus 2 to the 4th, plus minus 2 squared, again, because we have x here is raised to the 2nd power, minus 3 times negative 2. That's 3 times our lower limit is negative 2. And simplifying all of this, we can verify that you should come up with negative 123 over 4. For the next example, we're asked to evaluate the following definite integral. That is, the integral of 3x squared of 6x squared plus 1 dx evaluated from 0 to 2. For the solution, we let u here be equal to 6x squared plus 1. Then, if we try to take the derivative of u, you will come up with 6 times 2 will give you 12x, plus the derivative of 1 is 0. So you will have du is now equal to 12x dx. But notice that you only have 3x dx here. So to be able to get this value, we can divide du and 12x dx by 4 and come up with 1/4 du equals 3x dx. So you now can see that you can substitute your 3x dx by 1/4 du, and your u here is equal to u to the 1/2. Now, we try to take a look at the limits of integration. Because we substituted u to be equal to 6x squared plus 1, then we have the following. When the value x equal to 0 is substituted to u, to x, then you will have 6 times 0 squared plus 1 is equal to 1. So you have u equal to 1. When x is substituted as 2 here, and x equal to 2, you will have, because you have 2 here, you will be able to solve for u to be equal to 6 times 2 squared, that will be 6 times 4, that's 24, plus 1, that's equal to 25. So meaning to say, the limits of integration also changes from 0 to 2, it will become from 1 to 25. And rewriting, we now have the following. That is, the integral from 0 to 2 of 3x squared of 6x squared plus 1 dx now becomes, you have from, when x equal to 0, you have u equal to 1, so you have 1. When x is equal to 25, when x equal to 2, you have 25, so you have u 25. So 1/4 square root of u du is equal to 1 over 6 u raised to the, what happens here, why do we have 3 over 2? This is u to the 1/2. So 1/2 plus 2 over 2, that becomes 3 over 2. And then it should be over 3 over 2. But because we have 1/4 here, so over 3 over 2 can be written as 1/4 times 2 over 3. Then you can cancel out your 2 and 2 here. So come up only with 1 over 6. And then you have 1 raised to the, this is evaluated from 1 to 25. When you do that, you now have 1 over 6. Your u is replaced by this u here, 25, the upper limit, minus 1, the lower limit, is raised to the 3 over 2 also. So simplifying this, it should give you the value 62 over 3. For our next example, we're asked to evaluate the following definite integral. That is the integral of sine x plus sine x cosine x dx evaluated from 0 to pi over 4. Notice that we have a sum here, so you can write this as, can take individually its integral. That is the integral now of sine x dx evaluated from 0 to pi over 4 plus the integral of sine x cosine x dx evaluated from 0 to pi over 4. Then we can let u be equal to sine x, and we know that the du is equal to cosine x dx. And then when this value here, when x is equal to 0, because sine of 0 is equal to 0, you will have u is equal to 0. And when x is equal to pi over 4, we have here, you can replace here sine of pi over 4, but sine of pi over 4 is equal to square root of 2 over 2. That's why u now is equal to square root of 2 over 2. So by substitution, we now have the following. That is, we have sine x dx here, the integral of sine x dx from 0 to pi over 4, plus the integral of sine x cosine x dx from 0 to pi over 4. We know that we can actually solve for the integral of sine. Integral of sine is negative cosine. But here, since we make use of substitution, wherein our sine x is equal to u, and our du is cosine of x, so we'll have the u there. But u du, when you integrate that, this is understood to have an exponent 1, that becomes u squared over 2. So that from here, the integral of sine is negative cosine x, evaluated from 0 to pi over 4. So this one here is, its integral is 1/2 u squared, evaluated from 0 to square root of 2 over 2. Simplifying further, we have negative cosine of x, so the upper limit there is pi over 4. So negative cosine of pi over 4, but cosine of pi over 4 is square root of 2 over 2. Then we have minus of minus, it becomes plus there, cosine of 0, which is equal to 1. Then we have 1/2 u squared, So 1/2, our u is this time square root of 2 over 2. So you have the 1/2 square root of 2 squared over 2. When we square that, you will have 4 over, this is square root of 2 squared. That will give us, get rid of 2 there, so we'll have 4. And then this square, this one, when you square this becomes 2. 2 squared. This becomes 2 squared. Okay. So from here, we now have minus 0. So u squared, when you replace it with 0 squared, that's still 1/2 times 0 squared is still equal to 0. So if you try to simplify this one, come up with the following value, that is 5 minus 2 square root of 2 all over 4. You can actually verify this by solving for these values here. The next example, we have the integral of ln of x over x dx evaluated from 1 to e. Now, if we let u be equal to ln of x here, then our du, if you recall, the derivative of ln is 1 over x dx, correct? And then, note that when x is equal to 1 here, okay, when x is equal to 1, what will happen? ln of 1. So u becomes 0, because ln of 1 equal to 0. And when x is equal to e, you will have ln of e. But ln of e is equal to 1. That's why u is equal to 1. So by substitution, we have the following. The integral of ln of x over x dx from 1 to e is equal to, this time you replace your ln of x by u, and then dx over x by du. So we have the integral of u du from 0 to 1. Again, you have an exponent 1 there. That's u to the 1, so you can write it as u squared times 1/2. Or actually, that's u squared over 2, evaluated from 0 to 1. And that should give us, when we try to substitute, you will have 1/2. Then from the upper limit, which is 1, that's 1 squared minus 1. So 1/2 times the quantity 1 squared minus 0 will give us 1/2. Now for our last example, we are to evaluate the following definite integral. That is the integral of sine x over 1 plus cosine x dx evaluated from 0 to pi over 2. For the solution, we let u be equal to 1 plus cosine x here. Then, we can take the derivative of u. Derivative of 1 is 0. Derivative of cosine is negative sine x dx. Note that when x equal to 0 here, you will have 1 plus cosine of 0. But cosine of 0 is equal to 1. So you'll have 1 plus 1, that becomes 2. So u is equal to 2. And when x is equal to pi over 2, you will have u is equal to 1 plus cosine of pi over 2. But cosine of pi over 2 is equal to 0. So you will have now 1 plus 0, so u is equal to 1. So by substitution, we have the following. That is, the integral of sine x over 1 plus cosine x dx from 0 to pi over 2. You replace this time your 1 plus cosine of x to be equal to your du, your u here. And then sine x dx is actually du, but there's a negative. That's why you have negative du. Negative du is your sine x dx. This one, sine x dx. So that when we take the integral of 1 over u du, okay, then you have negative. Notice that this is 2 to 1. To make this positive, we can actually reverse the value here. That becomes positive, but you now have from the integral from 1 to 2 of 1 over u du. That's a trick there. You can replace, you can interchange the limits of integration, but you also have to change this value from negative, it becomes positive, but you have 1 to 2 instead of 2 to 1. And you know how to evaluate this, that integral, that is equal to ln of u, absolute value, evaluated from 1 to 2. And when you replace that one with f of b minus f of a, so it becomes ln of 2 minus ln of 1. So 1, ln of 2 minus ln of 1. But then we know that ln of 1 is equal to 0. So the result is simply equal to ln of 2. Now, here's the summary. For the summary or table of integrals, we have the following. So you can make use of this one to recall all the formulas. You have the integral of dx is equal to x plus c. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, if that is as long as n not equal to negative 1. The integral of a f of x dx is equal to, you can take out the constant outside the integral sign and just simply solve for the integral of the function. And if we have integral of the sum is the sum of its integrals, and the integral of e to the x dx is still e to the x plus a certain constant c. Notice that you only make use of the constant c if you have an indefinite integral. But if you have a definite integral, then you get rid of this constant c, and you simply substitute back the from the upper limit minus the lower limit, whatever the integral value you get. Also, the integral of a to the x dx is equal to a to the x over ln of a plus c. Note that if this value here is a function of x, then you will have a to the u du equals a to the u all over ln of a. Okay, so plus c. The integral of x to the negative 1 dx is equal to 1 over x dx is equal to ln of x plus c. Similarly, if this is u to the negative 1 du, then you should have the integral of 1 over u du is equal to ln of the absolute value of u plus c. And this, you can recall all these trigonometric integrals making use of the box that we had earlier. Also this, cosecant squared x dx, you have to memorize this, but there is a mnemonic device wherein you can actually recall all these formulas. As for this one, notice that the integral of dx over the square root of a squared minus x squared is equal to sine inverse of x over a plus c. If you remember, you also have here the integral of dx all over 1 squared minus x squared. But a squared is a more general value. So a can be any constant there, positive constant. Integral of dx over a squared plus x squared equals 1 over a tangent inverse of x over a plus c, and the integral of dx all over the square root of x squared minus a squared is equal to 1 over a secant inverse of x over a plus c.